Hello everyone, my name is Ben and in this talk I am presenting the results of a joint project between Manchester and the University of the West Indies on satellite observations of gas emissions during the April 2021 eruption of Soufrière St Vincent, and how we can use these measurements to identify precursory signals and improve our understanding of eruptive processes for eruptions such as this. Soufrière is a volcano situated on the island of St Vincent in the Lesser Antilles arc, as shown in the map here. It erupted explosively on the 9th of April 2021 after several months of effusive dome building activity. This picture shows one of the several eruptions which went on until the 22nd of April. These explosive eruptions are extremely hazardous, although thankfully in this case there were no casualties due to a timely evacuation, demonstrating how effective volcano monitoring is essential in managing volcanic risks. Identifying and quantifying gas emissions is a key part of volcano monitoring, but also for understanding the eruption dynamics during the eruption itself. However, this is tricky to do for these large explosive eruptions. In order to investigate the gas emissions from Soufrière, we turn to Trophome. This is a polar-orbiting hyperspectral sensor on board ESA's Sentinel-5P satellite. It provides us with daily, almost global coverage and is sensitive to several trace atmospheric gases, including sulfur dioxide. What is truly revolutionary about Trophome is its spatial resolution, which is only several kilometers square at nadir. This allows us to see much more detail in the volcanic plume, but also it allows us to detect much lower level degassing. Here I want to give a quick overview of the sensing principles of Trophome for those who aren't familiar. So here we have our volcano that emits some gas at a given time into our very rectangular atmosphere given by our blue box. As time passes, the gas is advected downwind by the three-dimensional wind field, at which point along comes our satellite. It performs its measurement as it passes over the plume and then continues on its merry way around the Earth again. This is an example of the raw output data from Trophome, which provides a daily static snapshot of the two-dimensional distribution of sulfur dioxide in the atmosphere. The issue here is that there is no information about the altitude of the gas, which is required for calculating the mass in each pixel, or the time it was emitted, and both these things are required to reproduce the flux time series. Luckily, we have a solution by using back trajectory analysis to determine these two factors. If we look at a single pixel, we can launch back trajectories running backwards in time from a range of altitudes, using NOAA's high split model with 0.25 degree global forecast system wind field data to see where they go. What we see here is that the trajectory initialized at the correct altitude, here shown in light green, passes closest to the volcano. Indeed, we can plot the closest approach distance of each of these trajectories to determine the correct altitude, as well as an estimate for our uncertainty in that altitude. This gives us our missing factors: the altitude that the gas is in the atmosphere, the altitude that it was injected, and the time that it was injected from the volcano, allowing us to reconstruct the SO2 emission as a function of altitude and time. So, what did Trophome actually see? This slide shows an overview of the SO2 emitted from Soufrière over its eruption, as seen by Trophome. We actually detect a precursory SO2 signal the day before the explosives activity, although it's difficult to see given the scale of these plots here. There was then an initial explosion on the 9th, followed by a jet emission phase, which morphed into discrete explosions over the following days. The plumes were truly vast and were detectable for several days circling the globe. Note that after the 11th, previously emitted SO2 recirculated back to the volcano and obscured the ongoing emissions, so we were not able to analyse past this point. So, onto our results. We were able to calculate fluxes for the precursory degassing detected on the 8th of April. Here you can see the raw Trophome data for the SO2 concentration, the cloud fraction, and the ultraviolet aerosol index, which is a tracer for volcanic ash, where positive or blue values in this case signify the presence of ash. Our results show that this plume heading towards the northwest was emitted at a fairly low altitude of around 3 to 4 kilometers, although this is still a few kilometers above the vent. And here we can see the emissions were stretching back to around 12 hours prior to the overpass of the satellite. Using this data, we can reconstruct the emission into a flux density plot, shown here. Here, darker colours represent a higher flux emitted at that altitude and at that time, with the top plot showing the integrated emission with time. We also show the RSAM time series measured by seismic stations throughout the eruption for a comparison. We can see that we measure fluxes of approximately 1 kg a second, or around 80 tonnes per day, in agreement with the boat traverse performed on the same day. Moving on to the 9th, we can still see some low-level early emission to the northwest. However, we are dominated by the main SO2 plume produced by the initial explosion. You can see our injection times line up nicely with the peak in the RSAM. The SO2 was injected over a roughly 2 km range of altitudes, causing the plume to spread out downwind into this hook shape that we see here. We calculate a total mass of approximately 2 kilotons emitted during this explosion, with a peak flux of 330 kilograms a second, or 28,000 tons per day. Using the injection altitude to estimate the mass eruption rate, we can also calculate an original magma sulfur content for this eruption, which comes in at approximately 0.0024 weight%. Then things really get interesting. The initial explosion was followed by this jet phase of continuous emission, which produced this massive plume that we see here on the overpass from the 10th of April. The plume was emitted at similar altitude to the initial explosion of roughly 15 kilometers, but we are now seeing peak fluxes of almost 7,000 kilograms a second, which is 600,000 tons per day, roughly 20 times that of the initial explosion. This produces a total mass of over 300 kilotons for this day. As before, we can estimate the sulfur content of the magma, and we now see numbers of roughly 0.052 weight%, at least an order of magnitude higher than that of the initial explosion. This suggests that the initial blast was a throat-clearing eruption, erupting previously degassed magma and clearing the way for the main undegassed magma source in the following explosions. And finally, we have the data from the 11th of April, where we see a continuation of the emissions at a slightly lower rate. The injection altitudes are also more spread out as we transition to discrete explosions as seen by the RSAM time series. We also calculate a lower but comparable sulfur content of 0.042 weight%. One thing to note here is the impact of volcanic ash on the sulfur measurements. You can see significant ash presence in the proximal plume as given by the positive UVAI values, and this produces a significant decrease in the measured flux in the hours before the overpass. And this is something to take into note when using these results for these ash-rich eruptions. So, to summarise, Trophome was able to detect precursory SO2 emission the day before the explosive activity began. During the main eruption, we can see a relatively SO2 poor initial explosion, followed by the main bulk of the emissions. This suggests that this initial explosion cleared previously degassed magma, which was followed by the main eruption driven by the fresh source. Presence of ash in the young plume does seem to have an impact on our measurements, but it does look to drop out rapidly. Thank you all for listening, and if you have any questions, I'll be around for the conference, or you can get in contact with me over email or Twitter using the details shown here. Thank you very much.